Take a moment here at the beginning to pause the video and read the question in its entirety. In this example, we will be solving applications involving exponential decay models. And the very first question asks specifically, what is the decay rate of this element? And we know that because of the form that this model is written in, the decay rate is K, this coefficient here of T. Written as a percent would be negative 2.44%. So that could be directly plucked from the model itself. Next, in part B, we're asked approximately how many grams of this element is left after 20 years. Now, to solve for that, what we would do is enter the information we know about this model. So let me do that here. So for instance, we know that the scientist has started with 800 grams. So the 800 grams is A sub 0, the initial value. So I can replace that with 800. E, of course, is the constant. And 244T now makes our model. So in part B, when we're asked to find how much of this element is left after 20 years, years being that time, T, we're going to replace 20 in our model, or replace T rather with 20 in our model like this. I missed a 0, hang on. There we go. And times T, or 20. So I can just simply input this expression into any calculator. Don't round if you're doing this in steps, but that's why I would suggest is type the entire thing in the way you see it into a calculator and then round at the very end. We should get approximately 491 grams is what A of 20 equals. So at time 20, there is 491 grams. That's what this expression or this equation here tells us. In part C, we're asked, when will there be only 200 grams of this element? So this is a little bit different direction here. This time we know A of T. We know the amount. So I'm going to replace that with 200. But I don't know T, the time that it takes to get to 200. So T is what's being solved for. Now, at this stage, we're really just solving an exponential equation. So to solve an exponential equation, steps always look this way, that we want to isolate the exponential piece first. That means move the 800. And think about it like this. How would you solve any equation for its variable? You would perform the inverse operations in order to isolate the variable. So I would have to do the inverse of multiply by 800 on both sides. So I would divide by 800 first. Okay, by doing so, we get 0.25 E, or equals E, to the negative 0.0244T. Then we want to do the inverse of the exponential form because we want to get this exponent, this variable, out of the exponent. So do the inverse of the exponential form. In other words, change this equation into its logarithmic form. Its logarithmic form is log base E of 0.25 equals the exponent, like this. Log base E can be further changed into natural log, because that's a very special logarithm, log base E. All right, so then, now it's a lot easier to get T by itself. I see that these two values are being multiplied, so to isolate T, I would just divide by negative 0.0244 on both sides And this is how we end up with T is approximately 56.8 years. Again, I suggest type this entire expression into your calculator just the way you see it. So that way you don't have to do a lot of rounding. You see, even in my math lab, it says do not round until the final answer. So anytime that you can just take the full expression with you until the very end, do that. Now, in the last part, we're asked to find the half-life, to find the half-life of this element. Okay, so half-life is the amount of time that it takes for the element to decrease by half. So in other words, if I have to start with 800 grams of an element, I want to know how long does it take before I end up with half of that, or 400 grams. So that amount of time is unknown as T. So you can see here I've just rewritten the exact same form or formula for this problem. I know that 800 grams are there to start with. That's the initial value. And I want to know how long, how much time, so I don't know that. I leave that as T. How long does it take before we end up with 400 grams, half the amount? This is the half-life. When I find that value T, that is the half-life. All right, so I'm solving here another exponential equation. So let's make parallels as we go between this one and the one that we have over here on the side. Let me zoom in just a little bit more. There we go. Okay, so again, we do inverses to solve for T. The very first thing we want to do is divide both sides by 800. We end up with 0.5 equals E to the negative 0.0244t. And by the way, this will always happen when we do half-life problems. If you think about it, no matter what you start with, you will purposely place half here as A of t, the output, and then solve for t. So every time that you go back and you divide, you should end up with 0.5. So that's kind of a little bit of a shortcut, I guess you could say. The next thing we want to do, notice that we did it back here too. We changed the exponential equation to a logarithmic equation. So this is going to be, I could say log base e, or just go ahead straight to natural log of 0.5 equals the exponent. And then last step, divide, because this is being multiplied. I want to do the inverse. And again, if I type all of this into my calculator, that I don't have to worry about rounding until the very end, and I get that t is approximately 28.4 years. So in other words, it takes a little over 28 years before half of the element has decayed. That is its half-life.